on Thursday that I'm still working on. Will be on gas laws as well. So I figure we might as well start with that. So, yeah, so we sort of left off just talking about the basic physical laws that describe how gases change. Yes, my dogs are busy at work. Change the physics of gases, and these are the basic variables we have to be familiar with. And so the ones that we should be familiar with are, let me get something to write with. So we've got pressure, and I think we understand, hopefully we understand what pressure means. Pressure just basically means the amount of force over an area. And could anyone tell me what physically happens with gases and their container to give us pressure? What actually happens with gas molecules and their container that results in pressure? Anyone know?
Don't we change the volume per square inch, for example?
Well, we don't have to change. No, basically, no, we don't have to change the volume. If we change the volume, yes, we change the pressure. But what is it about gas molecules and their container that results in pressure? Like what?
Oh, they're super, what's the word? The molecules are super far apart, so when you apply pressure, they get more condensed and start moving around and
moving around. That's a key. So there's something that those moving gas molecules actually do that results in pressure. Anyone think of what that might be?
Explode?
No, they don't explode. They're moving around. So we got all these gas molecules zipping around the container. But what actually happens?
When
they push off themselves? Like,
yeah, when they hit each other.
Nope, not when they hit each other.
When they hit the wall?
There you go, yes.
Okay.
So since gas molecules are moving so quickly, when they hit each other, it doesn't really result in a force against the sides of the container. So it's actually the force against the sides of the container that result in pressure. And so when the gas molecules actually collide with the sides of the container, that results in pressure. And so when we think about, since one of the things we're going to be learning about is the kinetic molecular model of gases. And when you think about these things sort of zipping around, the fact that when they hit the side of the container results in pressure actually makes a lot of sense when you think about the gas laws. Because let's think of it this way. If we have now twice as many molecules in the same volume, there are going to be twice as many collisions with the sides of the container. And so the pressure is going to go up by a factor of 2. So that's Avogadro's law. Okay, that makes sense. And if we increase the temperature, that means that the molecules are moving now even faster than they were before. And since now they're moving faster, they have more chances to hit the sides of the container than they did before. And so pressure is going to go up as a result of that. And if we change the volume, if we squish it down to half the volume that it was before, again, now we have twice as many molecules per unit volume that we did before, twice as many collisions with the sides of the container, and so our pressure is going to go up. So that's just basically how we resolve kinetic meaning movement. The more kinetic energy that we add to the molecules, or the more ways we can get molecules hitting the sides of the container, the higher the pressure. So increasing the temperature, decreasing the volume, or increasing the amount of gas. All three of those things result in a higher pressure. And so it's these four variables. These are the basic things that we're going to be measuring. We'll be measuring pressure, measuring temperature, calculating volume, and calculating the number of moles of gas. And remember, it's always going to be moles of gas, not grams. Because as someone mentioned earlier, there is so much space between molecules of gas, it does not really matter how big the molecules are. They pretty much all act exactly the same because it's basically the space in between them. So what an ideal gas is an ideal gas exhibits exact relationships between pressure and temperature, pressure and volume, pressure and number of moles. Would be like exactly a linear relationship. Not all gases, in fact, most of them aren't ideal, but they're pretty darn close to being ideal. So as the bottom note says, no ideal gas actually exists, but most of them act almost identically at the sort of temperatures and pressures we're going to be dealing with. At extremely low temperatures, extremely high pressures, you sort of get some weirdness happening. But with sort of the usual pressures and temperatures that we'll be dealing with, gases act pretty much in an ideal way. So any questions about how gases are, what the difference is between an ideal gas and a non-ideal gas? We will have some examples of non-ideal gases and how to deal with them a little bit later. Okay? So the first law, and we're going to be doing some experiments to show how this works. Just as I mentioned before, if you increase the volume, you basically now have fewer gas molecules per area than you did before. And so the pressure is going to go down because now there's more space for those gas molecules to move and not come in contact with the sides of the vessel they're in. And so if the volume goes up, pressure goes down. And exactly the same way, if you decrease the volume, you now have less space for those molecules to move around. And so they have basically more chance of coming in contact with the size of the container than they did before. So we would say that this is an inverse relationship. And it's important when we do the lab, we know the difference between an inverse and a direct relationship. So in other words, when it's inverse, as one goes up, as P goes up, V goes down. And if it's a direct relationship, that means they both go up and they both go down at the same time. And so if we have an inverse relationship, if we multiply them together, we should get a constant. And the constant will become really important when we talk about gas laws. We'll get to how we derive the constant in a minute. So that was Boyle's law. Charles's law shows the relationship between volume and temperature. And it's also important to remember temperature, when we deal with temperature, it's always Kelvin. It's always absolute. The reason is, because can anyone tell me what happens at 0 Kelvin? What happens to molecules at 0 Kelvin?
All molecular
stop
motion
moving.
stops.
Yeah, stop moving. And so when we're talking about gases, basically all of the properties we've been talking about so far about gases are all related to the fact that they move. Now, if the gas molecules can't move, there can't be any pressure because they're not moving. They're not able to hit the size of the container if they're not moving. But any increase in temperature above absolute 0, there is some movement. And so even at like something like helium doesn't become a liquid until I think it's around 2 Kelvin. like some incredibly insanely like cold temperature. So anything above like 2, it's still a gas, and those molecules are still moving, so you can still get pressure. So when we're talking about gases, it's always we're not talking about change in temperature, we're talking about absolute temperature because we're talking about the movement of molecules. So it's always in Kelvin, not in Celsius or in, well, definitely not Fahrenheit, but Kelvin is what we're going to be talking about. And so because it's the movement of the molecules we're dealing with, if we increase the temperature, we increase the kinetic energy of those molecules. The higher the temperature, the faster it is they're going to go. And so the faster it is they're going to go, if the pressure, and remember, this is important, Charles's law deals with constant pressure. I also can call this the balloon law. The easiest thing to remember is that when you're blowing up a balloon, the pressure inside the balloon doesn't change. The pressure is basically the atmospheric pressure that's around it, right? So as we blow up the balloon, we're adding more and more moles of gas, and the volume goes up. Same is true if we take that balloon, we tie it off, we increase the temperature of it, the volume gets bigger. So like if we put a balloon in a hot car, the balloon was actually bigger. And if we put it in the freezer, the balloon gets smaller because the pressure is the same. You still have 1 atmosphere of pressure, but we're allowing the volume to change because we have expandable, like a balloon or something like that. If the volume can expand, it will. And the volume will expand based on the temperature. And this is a direct proportion. So as V goes up, as temperature goes up. So those two of them are directly related. And so instead of multiplying them together, we would divide them by each other to get our constant. Because as one goes up, so does the other one. As one goes down, so does the other one. So if we divide them by each other, we get a constant number, okay? And then Avogadro's law, we can call this the sort of, balloon law as well. But in Avogadro's law, the temperature and the pressure are both fixed. And so basically, what Avogadro did was back in his day, he did reactions that resulted in the release of gas. Mostly, sort of some of the reactions you would do is you would take like a metal and react it with hydrochloric acid, and that gives you a salt and the release of gas. So what he would do is he would measure the release of hydrogen gas and notice that if he had twice as much magnesium, the volume of the hydrogen he collected was exactly twice as much. If he had half as much magnesium, the volume of the hydrogen he would get was exactly half as much. And so he realized that the molar amount of gas is directly related to the volume. So he'd do these experiments under a fixed temperature and a fixed pressure, and then notice that the volume, however many moles of gas were created, was directly related to the volume. So again, directly proportional. So we would divide the volume by the number of moles, and that would give us a constant K. So Avogadro was the first to notice that. So basically, when we take all of these laws and put them together, we get basically one overall equation that we can use. But before we get to that, we have to realize what we call standard conditions, because we have to relate this equation to something. And so what the standard conditions are: 1 atmosphere of pressure, that makes sense. That's because basically the atmospheric pressure is usually around 760 torr. Anyone remember what 1 torr is equal to? What's 1 torr? Where do we get that number from? What's 1 torr?
Was it the device that used mercury to measure pressure?
Right. So that is 1 millimeter of mercury.
Right. Yeah.
So if you have a column of mercury being subjected to atmospheric pressure pushing down on the mercury that's being pushed up a column. So the higher the pressure, the more it pushes the mercury up into the column. And at exactly 1 atmosphere of pressure that pushes the column of mercury 760 millimeters up. If it's less, the height of the column is smaller. If it's higher pressure, the height of the column of mercury is higher. And we just call that 1 millimeter of mercury, we call that a torr. And that's basically how scientists measure pressure, because basically all of our equipment comes in with torr. And generally, if you're pulling a vacuum, you measure that in like micro torr, or if you have like a really good vacuum, like nano torr, extremely low pressures, we measure in torr. And so, yeah, and so that's the standard pressures, 1 atmosphere. Standard temperature is a little different because usually we've been thinking about the standard temperature for most things in chemistry is 25 degrees C. For gases, it's 0. And in Kelvin, 273 K, okay? So the standard volume for 1 mole of gas, and it doesn't really matter what gas it is, an ideal gas, at STP, or standard temperature pressure, is 22.4 liters. So it doesn't matter what gas it is. If I have 1 mole of gas at 0 and 1 atmosphere of pressure, it's going to take up 22.4 liters of gas, or of volume. So you don't have to remember this. If I give you that on a test. But what I'll expect you to do is, like, if I do a reaction, say like Avogadro did. Avogadro did a reaction. He collected liters of gas. Is everyone okay there? Oh, mute. So if Avogadro collected so much volume of gas, like say 75 milliliters of gas, you would then have to use this function to calculate how many moles of gas, okay? All right, so this gives us basically another way of looking at the standard molar volume. Remember, it doesn't matter what the mass of the gas is. If I have 1 mole of helium, if I have 1 mole of nitrogen, if I have 1 mole of oxygen, doesn't matter what the mass is, they're all going to have the same volume, okay? So here, helium weighs 4 grams per mole, 8 grams per mole. Oxygen is 32 grams per mole. It doesn't matter what the mass is, because the distance between those molecules is so large, the mass of the molecule in the middle doesn't really matter. It's the distance between them that really matters. And the number of gas particles that gives you, and so for 1 mole, like we said, they're all 22.4 liters. And that comes to the overall expression for the ideal gas law. And I just call it Pivnert. Ever wonder, Pivnert will give you what you need to get. Basically, whatever the pressure is times the volume, that is related to the number of moles, which is N, and the temperature. And it's all held together by a constant. So the constant relates to the number of atmospheres, the number of moles, the temperature, and the volume. So it has, man, thanks for sharing, whoever that is. So it relates the pressure, the volume, the number of moles, and the temperature. So the constant here is going to have 4 different units in it. Okay, before we've been dealing with 2 units or 3 units. This one's a big one. This one relates 4 different things. And so if we take this equation and we move everything to one side, we just leave R by itself, and we have PV divided by N. Where's my eraser? So PV divided by N and divided by T. That gives us this expression down here. So R is going to have the units for pressure, atmospheres, for liters, for volume, moles, for the amount of gas, and K for the temperature. And so we put all those things together. So at 1 atmosphere, for 1 mole, at 0 degrees C, and how much volume 1 mole of gas takes up. Put all those together, this is what we get for R. And again, I'll give you this, you don't have to memorize this, I'll give you that on a test. But what you will need to do is, you may not get liters in liters, you may get volume in milliliters. So you'll have to remember to convert to liters. You'll have to remember to convert Celsius, if you're given Celsius, to K. And if you're given grams of gas, you're going to need to convert that to moles. If you're given torr, you're going to need to convert that to atmospheres. So it's basically, you need to remember that, how do I get atmospheres? How do I, from torr? How do I get liters from milliliters? How do I get moles from grams? And you've been doing this long enough, you should be able to do moles to grams back and forth pretty easily by now. And Kelvin, fairly straightforward, just add 273 to whatever the temperature is in Celsius. And so again, you should, if you can't, I don't want you to memorize these things either, but I do want you to know you're going to have to do that. So I will give you the conversions. Your job will be to remember, oh, right, I need to do those conversions. If you see degrees C, know that you're going to have to convert them to Kelvin, okay? So what else you're going to need to do with this, because you see this equation is rather simple. But the tricky thing about it, you're going to be able to convert it and roll it around. Because again, here at the bottom, you can change this expression in a lot of ways. Because since R is always going to be the same, if we change to a new pressure, or we change to a new number of moles, or a new volume, or a new temperature, it'll always equal R. So if I change the pressure of something, I can calculate everything else. If I change the number of moles, I can calculate everything else. If I change the temperature, I can calculate everything else. By my initial pressure times my initial volume divided by my initial number of moles times my initial temperature will equal all the new things changed. So P2, V2, N2, T2, I can calculate all those things because I know that whatever I change is also going to be equal to R, right? So if my pressure goes up, I can calculate everything else that takes place. If my number of moles goes up, I can calculate everything else that takes place just by remembering this particular expression right here. And if you ever wonder where that expression comes from, just remember R is a constant. And so PV divided by NT is what you're trying to calculate to get back to the constant R. Any questions about how we get the universal gas constant calculated? Yeah, if you for some reason you sort of blank on what it is, if you can remember what the molar amount, what the volume is for 1 mole of gas, you can always go back and recalculate it. But yeah, I will give you this number. I will give you R, so you won't have to calculate it yourself. But I just want you to see where it comes from. So let's just do a quick problem, see if you're paying attention. So this basically like a balloon, like I sort of mentioned before. If you change the pressure or you change the temperature, the volume is going to change, right? So and I've been to the summit of Mount Hood actually. So if you have it's your birthday, and for some reason someone gives you a birthday balloon and then takes you on a hike, why not? Why wouldn't you? So you've got a really big balloon. So 15.8 liters is a big balloon. So, and the pressure at the bottom of the mountain is a little less than 1 atmosphere. So it's, which means it's probably raining. It's Oregon. It's probably raining. So the atmospheric pressure is a little lower than normal, and it's 22 degrees Celsius. So if you hike all the way up to the top of the mountain, where you can see the atmospheric pressure is less, quite a bit less. Mount Hood's pretty tall, and the temperature is now 0. What happens to the volume of your balloon? So here, there's 2 things changing. So you look at the volume it was at the beginning, so it's 15.8 liters. We know what the temperature was at the beginning, 22 degrees, and we know what the pressure was. So at the second, when you get to the top, the question is, what's V2? We don't know what that is. That's the question. What we do know is the change in temperature. We know what the new temperature is, and we know what the new pressure was. So remember, N stays constant. We haven't added any new amount of helium. We haven't released any amount of helium. So N stays the same. So I'll give you a couple minutes, see if you can come up with what is the new volume. Now remember how to PV equals N over T. So P1 V1 equals N1 T1. And that's going to equal P2 V2 N2, which is the same T2. So we know everything except this. So give you a couple minutes to see if you can come up with an answer for that one, okay? Remember, we need to did the conversion for you here for the temperature. You do need to convert the pressure. So I should be hearing lots of calculating going down. Anyone come up with anything? Here's some calculating going on. Must be getting close. So I'll basically ask a question. Do you think it's going to be bigger or smaller? And everyone's too busy calculating. So do we have a number yet?
Seems like it'll be smaller.
Well, it's kind of hard to tell, right? Because since the pressure went down, the volume should get bigger. But the temperature also went down. So that means the volume should get smaller. So we don't really know which one. Is it because of the temperature or because of the pressure? One makes it bigger, one makes it smaller. Let's see. All right, so this is how we would do it. So, as I mentioned, N stays the same. So we can eliminate that. So basically P1 V1 divided by T1, that's going to be a constant. And it's going to be the same as the new pressure times the new volume divided by the new temperature, because they both equal R. So to solve for V2, we just move pressure and temperature over. So V2 will equal V1 times P1 T2 P2 T1. Basically, the ratio of the pressures and the ratio of the temperatures. Now, because the pressures are inversely proportional, we have the new pressure on the bottom and the old pressure on the top. And because the relationship with volume is direct, we have the new temperature on the top and the old temperature on the bottom, because one is directly related, the other is indirectly related, right? So here's our pressures. We change the amount of pressure in mercury. 532 millimeters of mercury is equal to a torr. We know that 1 atmosphere is 760. And so the pressure, the new pressure at the top of the mountain is 0.7 atmospheres. And so that means that since the new pressure is lower, that's going to increase the volume by this much. Now the relationship with, as I mentioned, the relationship with temperature is direct. And so this is the change in temperatures. So the pressure change is going to lead to an increase in volume. The temperature change is going to lead to a decrease in volume. So it's basically which one is greater. And we can see that the change in pressure is greater than the change in temperature. And so you multiply them all together, it's larger. Yeah, the change in pressure has a larger effect than the change in temperature. And that's usually the case, unless you have like a huge change in temperature. Small changes of temperature, like 30 degrees or 40 degrees, it's not going to be nearly as much as a change of like 30% in the pressure. To change the temperature by 30% would be a really big change as far as the number. So does everyone see how we would do something like that? Just a matter of remembering what equals R. So if we remember our old Piv nerd, if we remember this, so we should just, we should have this like, tattooed on our forehead backwards or something. Just remember, I could always figure out what the relationships are between pressure and volume and temperature and number of moles just by remembering this expression. Because R will equal PV divided by NT. So this tells me pressure and volume are inversely related because we're multiplying them together. Pressure and temperature are directly related because we're dividing them. And pressure and number of moles are directly related because we're dividing them. So you can always work out what the relationships are just by remembering good old Piv nerd. So does anyone have any, man, I need to draw on this a little bit more. Anybody have any questions about how to, this is like sort of basic gas problem, doing a conversion from one to another. Something on the chat. Is there a question?
Somebody asked,
So the question was, this person got 0.688 for pressure. When do you round up?
Yeah, actually, that's a good point, because I would have used 0.688 as well. This is a slide I grabbed from someone else. Let's look at the number of significant digits. That's a really good point. So volume, we've got 3 significant digits. Temperature, I've got 2. Pressure, I've got 3. And temperature here, I've only got 1. So I think that as far as the pressure goes, I would keep my 3. I would keep my 3 significant digits. So this should be 0.688.
Wait, actually, it would not be 0.6 or 0.688 because I think she got the numbers wrong. I just plugged it into my calculator. If you divide 523 over
532. 532.
Yeah.
No,
It's
wouldn't it
532.
be 523 though?
Oh, it is
Because pressure-
523.
Yeah.
Oh, you're right.
She was right.
Oh, you're right.
It's
Okay.
523, and it's 532 here.
yeah, so the answer might be 20.
Oh, it is 688. It is 688 because it's 523. This number is wrong. Man, thanks for pointing that out. I'm going to change that slide. Yeah, thanks for pointing this out, because I've been looking at these, and I don't realize that there's some mistakes in here. So I will fix them. Yeah, so as far as basically what it comes down to, yeah, you've only got 1 significant digit for temperature, which is kind of rude. Basically, yeah, I would have probably rounded this to 2 significant digits based on the temperature. But when I give you a problem like this, yeah, I probably won't give you like 0. I'll give you at least 2 significant digits. So then you would then round this final answer to like, 21 liters or whatever it is. If you use, I would use this amount for the atmospheres. And I would then, that's the tricky thing with with just one significant digit. I'll give you at least 2 significant digits for the temperature. So your final answer should have 2 significant digits in it. But yeah, good point. I'm definitely going to make some changes with this. Because yeah, that's 0.7 atmospheres doesn't make any sense when you've got 3 significant digits for the pressure. Yeah, it should have at least 2, if not 3. So yeah, good point. So one more. So here, I've got a steel tank. Here's my volume. So obviously the volume's not going to change. It's a steel tank. So I got 438 liters. I used to have a tank like this in my lab at UCLA filled with liquid nitrogen. And about every, I don't know, hour or so, it would vent the pressure because it was, you know, it was liquid, and it would turn into a gas, and the pressure would get higher and higher and higher, and then it would have to vent. It would just scare the hell out of everybody because you never knew when it was going to do that. It was really loud. So you have a big steel tank, and it's filled with that much oxygen. So presumably this is not going to be liquid oxygen. It's going to be gaseous oxygen. So what is the pressure? So here we got 2 significant digits for the temperature, and we need to figure out, so we know what the volume is. That's not going to change. But we know what moles are, and we need to figure out P. So in this instance, we use a good old Pivnert. We know what this is. We need to calculate what this is, and we know what this is, and we have our constant. So basically, it's just P equals nRT divided by V. So you have to figure out the number of moles of oxygen, because we always deal with moles. R is given, and you need to calculate what the temperature is. So again, I'll give you just a couple of minutes to work on that. First of all, how many grams of oxygen do we have? Because remember, this is kilograms. How many grams of oxygen do we have?
880.
885, right. Because grams are small, kilograms are big. There's 1,000 grams in a kilogram. So we've got 885 grams of oxygen. So how many moles of oxygen do we have? What's the molar mass of oxygen? And remember, when we're dealing with gases, pretty much, except for the noble gases, pretty much all the gases we're going to be dealing with are diatomic, right? Because we've got H2, we've got N2, we've got O2, we've got Cl2, we've got Br2. So pretty much all of them are diatomic. So if we're figuring out how much a mole weighs, remember, it's the molecule, not the atom. We need the mass of. So for oxygen, how much does a mole of oxygen weigh? What's the mass of a mole of oxygen?
16, isn't it?
Oxygen molecules. 32, exactly. A mole of oxygen atoms is 16, but a mole of oxygen molecules, which would be the gas, O2, so that's the most stable form of oxygen at STP, at standard temperature and pressure, is O2. So that would be 32 grams per mole. That'll give us the number of moles anyway. 885 divided by 32, 27.7 moles. So now we know the moles, we know the volume, you know the temperature. What's our temperature? How do we convert Celsius to Kelvin?
You add 273.
Yeah, or 273.15. You can, I like to use all of the significant digits I have and then round it at the end. So 273.15 plus 21, 284.15 Kelvin. So now you just need to remember what R is, and you're good to go.
It would be 294.15 for temp. For Kelvin, it would be 294.
Oh, 94. Oh. Yeah, see, that's what happens when you try and do things in your head and you're old and easily confused. Yeah, 294. Yeah.
Isn't R the universal gas constant?
Yep, it sure is. It is universal and constant. So what's going to be the pressure? Oops. Oh, I don't want that. Oh, here we go. So if we got a answer.
154.41.
That's not an answer. What
18.603
That's not an answer either. What does an answer need?
measurements.
Units, yes. So a number is meaningless without a unit. What's the unit?
ATM.
Which is what?
Atmospheric pressure.
Right. So you had what, 18 you said?
18.603. Oh, that's not right. Okay.
So this is our, maybe just didn't have the right units for R.
Yeah, I didn't put R.
Yeah, got to have R in there. Yeah, so we figured out how many moles. We figured out, we've been given the volume, and we calculated the temperature. So it's just a matter of putting the right value for R in there. And you can see that's about 50% higher than regular atmospheric pressure. Yeah, so here it's just a matter, you don't even, it's just good old Pivnerd, and just plug and play. You just need to remember what R is, and you'll have R on a test. Yeah, maybe I should probably have put R here so you could figure it out. But yeah, so that's, for these sort of questions, yeah, it's pretty much all it is just manipulating Pivnerd. So if PV equals nRT, it's just a matter of moving things around until you solve for whatever particular measurement you have to solve for. If you need to solve for P or solve for V or solve for N or solve for T, it's just a matter of manipulating that equation and moving everything that's known to one side and everything that's unknown to the other side and doing the calculation. Any questions about that one? This one should be actually easier than the previous one. I should change the order of these. So let's talk about density for a minute. So the density of a gas, when we talk about density, we're talking about like grams per volume, right? And so the density of the gas is directly proportional to whatever the mass of it is. And it's inversely proportional to the temperature. So if the temperature goes up, the density goes down. Because as the temperature goes up, more space in between the molecules, and the density is going to decrease. So another way to write this is that the density is equal to the mass over the volume, that's just how we calculate density in the first place. And so this capital M here is the molar mass, which is a little confusing because we think of that as molarity. And I think what happens is that usually this is written in italics or something. But what I'll do is I'll change molar mass to mm, because that is a little confusing. So moles is just whatever the mass is divided by the molar mass, right? That's always how we calculate moles. So we have Pivnert here, and we just take the mass divided by the molar mass, because that's what N is. That's the number of moles, right? And then it's just a matter of switching these things around. So if the mass over the volume is equal to the density, which it is, right down here, that's equal to the density, the molar mass times the pressure divided by RT also gives us the density. It's basically a way we can figure out what the density of the gas is using the ideal gas law. And so it's just substituting different things. So if we know what the molar mass is, we know what the mass of the gas inside a particular volume, we can measure the density, or we can use the density to figure out what the molar mass of a gas is. It's just exchanging one thing for another. Let's give an example of how that would work. So trying to get a way of recycling waste CO2. And chemical engineer, and that might be a gig some of you are interested in later on, use waste CO2 from a manufacturing process. And instead of using chlorofluorocarbons, which if you don't know if you remember, probably this was before a lot of you came along. They used to deplete the ozone in the atmosphere. They're called CFCs. Back in the old times, CFCs were actually used in aerosol sprays because they they do a great job they have very high pressure. And so they're great for, spraying on hairspray like we used to do back in the 80s. So anyway, instead of using that, which depletes the ozone layer, they want to use carbon dioxide. So find the density of carbon dioxide at standard pressure and temperature and room temperature at 20 degrees. So how do we go about doing that? We want to find the density. So first thing we need to figure out is what's the molar mass? Of CO2. So how much does a mole of CO2, what's the mass of a mole of CO2? Anyone have that off on the top of their head?
28.01.
I don't think so. The mass of carbon is 12. The mass of oxygen is 16. And there's 2 of them.
44.01.
There you go. So 44.01 grams. Now, we should remember at standard temperature and pressure how much a mole of CO2, what would be the volume of a mole of CO2? Anyone remember what at STP? A mole of any gas has the same volume. Remember?
22.4.
There you go. So basically what we're figuring out here is that 1 mole of CO2 at STP is 44.01 grams divided by 22.4 liters. And that gives us grams over liters, which is density. So at STP, what's the density? I mean, you have all the information you need right there. There's so we just assume we have we assume we have 1 mole of gas, because that just makes our calculations easier. So we have 44.01 grams, and we know what the volume is at standard temperature and pressure. It's 22.4 liters. So what in grams per liter, what's our density?
$1.96.
Yep. 1 point, that's Frijon, right?
1.96 grams per liter.
There you go.
0.96.
A number is just a number. Got to have a unit. Right.
Did someone answer that already? Sorry, my computer was lagging.
So yes, 1.96 grams per liter. 1.96 grams per liter at standard temperature and pressure. So, but at usual conditions, like at a normal room conditions, it's still 1 atmosphere, but the temperature goes up. So if the temperature goes up, what happens to the density? Does it go up or down?
Down.
Right, it goes down because it should increase the volume. So at 0, here's what we have. So this is our temperature. That's our pressure. And that's our molar mass. Right? So we figured that part out. So we plug everything in and we get our 1.96 grams per liter. But if we change the temperature to 293, now we've increased our temperature. How's that going to change our density? Now, instead of doing the entire equation, you could also do it another way by figuring out, since the density goes down as the temperature goes up because it's inversely related. Basically, all we need to do here is plug in what the new temperature is and the old temperature is, right? So we can take our old temperature, which was 273, and we take our old temp, that's our old temperature, and our new temperature is 293. Because we know that as the temperature and the density should be inversely related, right? So as one goes up, the other one goes down. So as the temperature goes up, our density should go down. So this should be by this ratio. So we can just take our old density, this times our old density, 1.96, and we should get our new density. So we'll do it this way, and we'll see if it agrees with doing it by plugging everything back in. So what do we get for this? So what's our new density as the temperature goes up?
1.82 grams liter.
I got 1.83, but okay. Now, yeah, because with the gas laws, a lot of it, if nothing else changes, if my pressure doesn't change, if my N doesn't change, if a lot of things don't change, it's just a matter of figuring out, well, should it go up or should it go down? Is it inversely related or is it directly related? And we know that with pressure and volume, pressure is inversely related, or pressure and volume are both directly related to the temperature. And since density has volume on the bottom, we know that the density and the temperature should be inversely related. It's 1 over volume. So it's just a matter of figuring out with my new temperature, with my new pressure, with my new volume, is it going to be inversely related or directly related? So 1.83. Let's see if hopefully we should get the same answer. Let's keep our fingers crossed here. Yeah, so we plug everything in, we get the same answer. Thank God. So yeah, so a shortcut would be just remembering whether things are inversely related or directly related. And that will save you a lot of trouble and having to plug all this stuff in. Because remember, we didn't need any of this stuff to figure out the answer. All we needed was the old temperature and the new temperature, and we get the same answer. So any questions about how to do that? If you don't know, if you can't remember how to deal with inversely or directly related, just use Pivnert and just figure it out. But if you remember that pressure goes up as temperature goes up, volume goes up as temperature goes up, you can figure out whether to put the new value on top or on the bottom to see whether it goes up or down. Any questions? Is everyone thoroughly confused at this point? Excuse me. Everyone's quiet. If you're quiet, I'm going to figure you're all geniuses and understand this completely.
So the important like concept is to learn is how you should manipulate that.
This whole this entire chapter is how to manipulate this equation.
Got it.
That's it. If you're really good at algebra, and that's true for like pretty much all chemistry, really. If you're good at algebra, you're going to be good at chemistry. If you don't understand algebra, you're going to be in trouble, because it's just manipulating equations. And so if you have the equation, there's so many things you can do with it. And one of the things you can do with it is figure out the density of the gas just by manipulating that exactly the same equation. And we're going to be using this, this equation over and over and over.
And just to clarify really quick,
Mm-hmm.
it's possible. So if you're missing a variable within that equation, it's possible that you're able to manipulate that equation to find that hidden variable. Correct?
Yeah, exactly. If there's one variable you're missing, you can always figure it out because you have the other three. So there's always 4 things we're measuring when it comes to gases: the amount in moles, the volume, the temperature, the pressure. So if you have any 3 of those, you can always figure out what the 4th one is. And so if you change one, just, it's a matter of just, figuring out how that one change manipulates everything. Or if you change 2, or even if you change 3, it's just a matter of, plugging them into that equation and figuring it out. Because R is basically, the genius of it is that R is always going to be the same. And so PV divided by N over T is always the same number, always. So we can always use it to come back and figure out any change. Yeah, so it's basically, that's why I find this particular chapter to be pretty straightforward, because basically all it is changing that one equation and being able to manipulate it. And if you can manipulate that equation, you've got it.
Okay.
Yeah.
Just out of curiosity, is that universal constant of the gas law, is that always going to be that number? Or like, how did you even get that, just out of curiosity?
Oh, let's just go back. Oh, here it is. Yeah, it's just based on at 1 atmosphere for 1 mole of gas at 0 degrees, what's the volume of a mole of gas? And that's it. We just plug all those numbers in. So at 1 atmosphere and 1 mole at 0 degrees, so here's our pressure, there's the number of moles, there's our temperature, and that's how many liters 1 mole of gas takes up. And you just plug all of that into what's the relationship between them. And you get this number here. It's basically 22 by 273. And that's it. So if you can remember, basically, if you can remember how many liters there are for 1 mole, which is 22.4, and you remember what the temperature at 0 degrees C is, 273 Kelvin, you can calculate what R is. That's all it is. It's just the volume divided by the temperature. And you leave,
So like
you leave atmospheres as 1, moles as 1. So it's just the number of liters divided by the temperature.
Okay. Just out of curiosity again. Do we always have to show the work for R, or if you're able to remember that number and the units, do we just apply?
No, I'll give you that. No, I'll give you that.
Okay.
Yeah, no, you don't have to remember it. Remember, I don't want memorization bad. Memorization bad for your brain. Understanding good. So yeah, I'll give you these numbers. I just want you to know how to manipulate. It's really how to manipulate that equation. That's the most important part. How we got it, but if, like you said, you were curious, like where it comes from. It's a simple matter of measuring how much gas, how much volume 1 mole of gas takes up, and that's actually that would have been one of the experiments we were going to do. We were actually going to do that very same experiment that Avogadro did by taking magnesium and dissolving it in hydrochloric acid and calculating how much hydrogen gas it created. You're actually going to calculate R yourselves. And from previous classes, people got really close by measuring the temperature of the water, because you do this underwater, so you could capture the gas. And by measuring the we would measure what the atmospheric pressure was in the room. And people got within like 5% of the actual number. So yeah, it's basically just calculating the how much volume 1 mole of gas takes up, and then that's it. Once you've got that number, you can just calculate R very, very quickly. So I'll have to come up with a online experiment sort of like that. All right, so before we go, let's just, all right, we figured out our density. 183. So we could figure out what the molar masses are from the ideal gas law. So here you can see that it's in italics. I think what I will do is change it to MM, is to try to relieve any confusion. So because N, number of moles, is equal to the mass of a gas, and this is the molar mass, this is how the actual molar mass of gases were calculated using this particular equation, because it's difficult to measure the molar mass of things. Excuse me. If, like, for instance, a lot of gases, like noble gases, you would normally figure out the molar mass of something by measuring the mass of it, doing a reaction, and then calculating the mass of the product. And that way you can figure out how many moles were in the original mass. So if I had a solid, I would weigh out mass of solid, I would react it with something, and then I would measure the mass of the product. And that way I could figure out how many moles of I started with, compare that to the mass that I weighed out and get the molar mass. For something like argon or helium or something like that, it doesn't react with anything. And so it's really hard to figure out what the molar mass of those are. But using the gas laws, we can figure it out because we know what R is. We can measure the pressure and the volume of a certain mass of gas, and that will tell us what the molar mass is. Okay. So an example here, I'm just going to leave you with this, and we'll figure out what the on Thursday. So this is an example of trying to figure out what the molar mass of a gas. So an organic chemist has got some colorless liquid. She doesn't really quite know what it was. It's like a petroleum sample. So she's probably like a petroleum engineer or something like that. She has this liquid, she puts it in a flask, boils the flask, so it vaporizes, and it fills the flask with gas. Because if it's petroleum, if you increase the temperature, it's basically going to turn into a gas. This is the volume of the flask. This is the mass of the flask with the gas in it. And then she measured what the mass of the flask was before she put the gas in it. So you can figure out what's the mass of the gas, okay? This is the temperature, and this is the pressure. And then, so using this, she was able to calculate the molar mass of that liquid. So just by vaporizing that liquid, she could pretty much figure out what it is. So it's a very easy, straightforward way of figuring out what the liquid is without doing any other experiments. Just basically, she just weighed it and then was able to calculate the molar mass. So I'm going to leave you with this, and we'll come back to it on Thursday. this afternoon, we're going to work on, I just posted in Canvas, the recitation number 10. And basically, it's all these noble gas questions, manipulating the equations. And this is basically one of those things you would use to manipulate, try and figure that out. So any questions before we call it an afternoon, and or call it a morning, and I'll see you at 1:15. Any other questions? Everyone's so quiet.
That looks good.
Okay. Good. Yeah, sorry about not posting the other classes as quickly. Yeah, just been a lot going on, and I got this new program I'm trying to figure out how to use. But yeah, I should have them all there by the end of the week.
I had a question, not related
Yeah.
to this class, but for summer school.
Okay.
The summer program, like the next chemistry class that's being taught after this one, is it going to be a total online format as well? That's how it's anticipated?
Yeah. I think all the classes at Skyline, I think, and across the county are all going to be online. So we're still trying to figure out what that means for the lab portion. Because this means, since this caught us all by surprise, we're basically, making up the online labs as we go. So we'll have, from what I've been hearing back and forth with the dean and everything else, we'll know a little bit more in like a week or two. But right now, we can say for sure that it's going to be all online.
Has there, and there may not have been just yet, but if you know, or when you know, can you let us know?
Oh, of course.
In terms of the four-year colleges, because some professional programs require in-person labs, so it kind of will dictate whether or not those of us that are looking toward professional.
Yeah. No. I know that's what the delay is working out. What Berkeley and San Fran State and all the other places are going to do, because they have those requirements, and it's like, well, there's nothing we can do about it right now.
Absolutely, there's nothing none of us can do.
Yeah, so I'm thinking that a lot of them are probably going to waive that. But I can't guarantee what someone at another institution is going to do. Hell, I can't guarantee what we're going to do. But
Now, of course, I just if you guys
no.
receive anything officially.
No, we're working on it. Yeah, because it's super important, because it's September's just around the corner, and hopefully things will be back to, it won't be back to normal for a really long time, but somewhat back to normal, hopefully. But we can't guarantee anything at this point. But good luck.
Thank you.
All right, so I'll see everybody at 1:15, hopefully, and I'll talk to you soon. Stay well, everyone.